Hi, everybody. Welcome to this session of Discrete Optimization Talks, or DOTS. We have one brief announcement. So this is our last DOTS of the season, but we do plan to bring DOTS back in the fall semester, but enjoy your summer break. From this point on, you've noticed that DOTS are now under a different mailing list. This is kind of coincidental, but it happens to be that we are also now being organized as part of the Mixed Integer Programming Society, which is it's a section under the Mathematical Optimization Society. So we've been acquired. This is a very big deal in the startup world, and so we are very happy about this turn of events. Yes, I encourage you to all join the Mixed Integer Programming Society if you haven't yet. If you've attended the last three MIPS, one of the last three MIPS, I think you're automatically a member, but you're able to join anyway if you would like. So that website is mixedinteger.org. Now, I'm very happy to introduce our first speaker of the day, Yatharth Dubey. He is currently a postdoctoral researcher at Carnegie Mellon University under the supervision of Dr. Gerard Carnegie. Now that pronunciation may be Georgina will help me with later. Essentially, there's another transition happening, which is that today is one of his last days, basically, at Carnegie Mellon, and he is going to be moving to his tenure track position at UIUC, University of Illinois, at Urbana-Champaign. Broadly, his research concerns with strengthening our understanding of algorithms that allow large-scale decision-making to be discrete decision-making to be better, in particular the algorithms underlying MILP solvers, which most of the people in this seminar are very hold dear to their hearts. Yatharth studies both theoretical and practical aspects of branch and bound and cutting planes to better solve MIP problems occurring in operations research. And Georgina will talk about some of those MIP problems occurring later on. An interesting part of Yatharth's abstract is that there are three sides to the story today. There's a negative side, there's a positive side, and there's a computational side, which I don't know how it fits in with the value judgments on the negative or the positive. So I'm looking forward to hearing these three sides of the story. Yatharth, go ahead.
Okay, great. Thank you, Alex and Elias, for the introduction and for inviting me to give this talk. I'm a big fan of the seminar series, so I'm especially excited to be here. Today, I'll be talking about a theoretical and computational analysis of strong branching. And this is based on joint work with Shantanu Dey and Prachi Shah at Georgia Tech and Marco Molinaro at PUC Rio. So the main object of study in this talk is the branch and bound method for solving binary integer programs. By binary integer programs, I mean the problem of finding a 0-1 solution to a given system of linear inequalities ax less than or equal to b that maximizes some cost vector c. And I probably don't need to sell a binary integer programming too much to this crowd. But as a reminder, it's a widely used tool in tons of application areas, including healthcare management, energy, logistics, and transportation. And the list is pretty endless. In 1960, Ailsa Land and Alison Doig invented branch and bound as a general purpose algorithm to solve integer programs. Today, it's become the workhorse of essentially all state-of-the-art IP solvers, including the familiar names Cplex, Gurobi, Skip, and others. And these are widely used by corporations in a variety of industries, as well as government organizations. And in fact, branch and bound has become the most commonly used tool for solving NP-hard optimization problems today. Still, despite its central position in operations research for several decades now, there has been a very poor theoretical understanding of many key aspects of branch and bound. So I'll give a brief review of branch and bound in the context of this talk. Branch and bound looks for an optimal integer solution by recursively partitioning the solution space. It starts by finding an optimal solution to a linear programming relaxation of the integer program. It then chooses a variable and creates two subproblems, each forcing that variable to be integer. It then chooses a subproblem to evaluate next and repeats. And the algorithm terminates when the leaves of this tree are all pruned. And a node can be pruned in one of three ways. The first is by integrality. The second is by bound. And the third is by infeasibility. Now, there are two main components that determine the execution of the branch and bound algorithm. The first is node selection. This refers to the choice of which subproblem to evaluate next out of potentially several open subproblems. An example of such a rule is the best bound rule, which chooses the subproblem with the best LP value. And this rule typically works well in practice and is well motivated by theory. And throughout this talk, we'll assume that when we talk about branch and bound, we talk about branch and bound that employs this best bound rule of node selection. The second and arguably more important component is variable selection. This refers to the choice of which variable to branch on. A simple example is the most fractional rule, which chooses the variable with the value closest to a half, maybe breaking ties arbitrarily. And there are several more sophisticated rules. In particular, the star of this talk is the variable selection rule known as strong branching, which we will introduce next. Instead of choosing a branching variable naively, strong branching does some computations at each node of the branch and bound tree to estimate what the best variable to branch on is. At each node, it assigns a score to each variable, capturing the bound improvement as a result of branching on that variable. So suppose this is the node we are currently evaluating. We first try branching on x1. We solve the LPs of the two child nodes. And we note the dual bound improvement on each side. So that's 2.7 to 2 on the left for an improvement of 0.7, and 2.7 to 2.5 on the right for an improvement of 0.2. And we somehow want to capture the improvement on both sides, but with a single number. So strong branching will then multiply the two improvements and set that product to be the score of x1, the variable x1. We then move on to the next variable. So now we try branching on x2. We again solve the two child LPs, do the same set of computations, and we see that the score of x2 is 0.34. After having done this for each variable, strong branching chooses to branch on the variable with the largest score. Okay? And it does this process at every node in the tree. The choice of variable selection can have an extremely significant impact on the size of the branch and bound tree. For example, Achterberg, Koch, and Martin considered 24 different instances and found that on average, strong branching results in a branch and bound tree that's an order of magnitude smaller than other common variable selection rules. And in some cases, this is actually several orders of magnitude. However, while the resulting branch and bound trees using strong branching are very, very small, it actually ends up taking quite a bit of time to achieve such a small tree. And we can see why this might be the case, right? At each node of the branch and bound tree, we have to assign a score to each fractional variable. And so for each fractional variable, we have to solve two LPs. So at each node, we may be solving up to like order n LPs. And this is essentially all that's been known about strong branching. That experimentally, it results in much smaller trees than all other known variable selection rules, but it tends to be pretty expensive computationally. And we aim to better understand this phenomenon in the hopes that this can lead to variable selection rules that result in small trees, but maybe without the same computational burden. In particular, we ask what allows strong branching to result in such small trees? How does it compare to the smallest tree for several classes of problems? And finally, is strong branching somehow provably good?
Yeah, quick question. Are you going to concern
Please.
yourself only with full strong branching?
Yes, in this talk, we will concern ourselves only with full strong branching.
Okay, is there any way to analyze strong branching that doesn't look at all variables? Or is that nearly impossible?
So we'll see in this talk that it's fairly tricky even to analyze strong branching for so maybe I can answer that a little bit
Sure.
towards the end of the talk.
Yes.
And then we can look back at kind of what I talked about. Yeah. Great question. Thank you. So we find that strong branching does very well in solving a fundamental combinatorial optimization problem in vertex cover. So vertex cover is the problem of, given a graph, we want to find a subset of vertices such that each edge in my graph is incident to at least some vertex in the subset that I selected. In fact, we want to find the smallest such subset of vertices that cover all of the edges. Okay, so the IP formulation of this problem, we have a constraint for each edge uv that says that we have to pick at least one of the vertices u or v. So here we'll consider a branch and bound tree that uses strong branching to solve an instance of vertex cover with additive integrality gap gamma. And by additive integrality gap, I mean the difference between the IP optimal value and the LP optimal value. Okay, so it's and then we prove this parametrized upper bound on the tree size of basically 2 to the 2 gamma plus a linear term. Okay, and this is for a branch and bound tree constructed using strong branching as a variable selection rule and the best bound rule for node selection. And the kind of sell here is that this is not true of branch and bound in general. In particular, there is a lexicographic variable selection rule and an instance of vertex cover where this lexicographic rule results in a tree such that this above upper bound does not hold. Moreover, the lexicographic tree has an exponential number of nodes, while the strong branching tree has at most order n squared nodes. So the takeaway here is that there are instances where strong branching provably results in much smaller trees than other maybe reasonable variable selection rules. So I'll give a quick proof sketch of the second result because I think it nicely illustrates how strong branching succeeds. Okay. So here's the instance we'll be looking at. So this is the graph, and we're looking at vertex cover on this graph. This instance consists of m identical subgraphs, like the one circled here. Okay, each subgraph has vertices A through C forming a triangle, A prime through D prime forming what we will refer to as a diamond, and the vertices A and A prime are adjacent. Okay, and we will refer to this subgraph in the circle as our gadget subgraph. Furthermore, the A vertices of these M subgraphs are connected to form a clique, as shown in the picture. Right? And this is the picture for M equals 4. A classic result of Nemhauser and Trotter guarantees that the all-half solution is both basic and optimal for the LP relaxation of this vertex cover instance. So we'll start by taking a look at how strong branching succeeds here. In particular, let's look at what strong branching does at the root node by evaluating what the product scores are for each vertex. So it's not too hard to see that any vertex in a diamond subgraph has product score 0. This is because there is an optimal solution to the LP that has already 0, 1 values on these variables. So no matter which of these variables vertices we branch on, one side will have no increase in the objective value.
But Yatharth, can I ask you a question?
Yes.
Empirically,
yes.
When people use strong branching, they try to avoid this, right? They say product, it's rather than the product of the deltas, you might do something like have an epsilon to safeguard against the 0 case, because then you throw away too much information. Like in practice, maybe one side improves the bound dramatically and the other doesn't move it at all, and you still want to consider some score for that.
Yes.
Right. So what are your thoughts about that?
Yeah. So that's exactly right. That is done in practice, and that's I won't mention it in this talk, but if you consider epsilon to be close to 0, in fact, in this case, epsilon even less than
half something.
I think in this case, I think epsilon even less than like order m, like strict, like asymptotically less than order m, will like the result will go through.
Still hold. Okay.
Yeah.
Thank you.
Yeah. Great question and great point. And And that maybe will be clear once we look at all of the product scores of the variables, right? Because we'll consider both sides of the improvement. So in this case, like if I branch on a vertex in a diamond subgraph, one side will have gap improvement 0, but the other side also crucially won't have dramatic gap improvement. It'll have gap improvement like 1-ish, 1 or half. Now let's consider the product score of this vertex 1b. In this case, the side fixing 1b to 1 only increases the objective value by 1/2, since the all half solution on the rest of the variables remains feasible. And the side fixing 1b to 0 enforces 1a and 1c to be 1. But again, every vertex outside of this triangle can keep its value of 1/2 and remain feasible. So again, the objective value increases by 1/2. And so the score of 1b and symmetrically 1c is 1/4. Finally, let's consider the score of 1a. So fixing 1a to 0 has a much more significant impact as it enforces its m+2 neighbors to all be 1. Right? And this increases the objective value by 1/2 m. Furthermore, the resulting vertex cover problem corresponding to the child node setting variable 1a to 0 actually has integrality gap at most 0, since the only variables that are not fixed in any optimal solution to this subgraph consist of disjoint edges and diamonds, which admit an integer optimal solution. And now let's consider the impact of fixing 1a to 1. So this still allows the all half solution on the rest of the graph to be feasible again. And so this increases the objective value by 1/2. And the crucial conclusion here is that the product score of this variable 1a is m/4. Furthermore, observe that the vertex cover problem corresponding to this branch and bound node fixing 1a to 1 consists of a disjoint diamond here, edge here, and a copy of the original graph with m-1 gadget subgraphs as opposed to m. Okay, so now let's look at what the strong branching tree will look like. Again, I just want to drive home the point that the product score of 1a here is significantly larger than the product scores of like JB, JC, or 1b, 1c, and then like all the diamond vertices, okay? So strong branching will choose to branch on 1a. So this is what the strong branching tree will look like, right? It begins by branching on x1a, since we showed that it has the largest product score at the root node. And the node fixing x1a equals to 0 has 0 integrality gap. And so the best bound rule instructs branch and bound to choose to branch on the node fixing x1a to 1, right? Since that has a better LP value. In particular, since the vertex cover instance corresponding to the node x1a equals to 1 is a disjoint diamond, edge, and a copy of the original graph with one less gadget subgraph, right? So again, this is the diamond, the edge, and then this is the copy of the same graph with one less gadget subgraph. We can kind of recurse the same logic and see that variable x2a will now have the largest score in this subproblem, and therefore will be selected by strong branching. And so the point is that applying this recursively, the tree will look like this kind of path of length m, until finally all leaf nodes in this partial tree have integrality gap 0. And fortunately, the parametrized upper bound of theorem 1 gives an upper bound on the size of the subtrees at each of these leaf nodes, right? Since each of these leaf nodes correspond to instances of vertex cover with 0 integrality gap, we have that each of these blue subtrees must have at most order n nodes. And since there are at most order n of these subtrees, we have the desired upper bound on the size of the strong branching tree. And it's pretty easy to find a branching rule it's pretty easy to find a branching rule that would struggle on a graph like this. In particular, any rule that prioritizes branching on vertices in the diamonds will require at least an exponential number of nodes, and in fact, even significantly more nodes than the upper bound on strong branching given by theorem 1. Okay. Now, these results, in particular theorem 1, follow from strong branching's ability to take advantage of problem structure, which in the case of vertex cover includes half integrality and persistency. I'll explain this in a bit more detail, but first let's define the persistency property, also called the Nemhauser-Trotter property. Consider an instance of vertex cover and let X star be an optimal solution to its LP relaxation. Then persistency tells me that there exists an optimal solution to the integer program, let's call it Y, that agrees with X star on all of X star's integer components. Now, why might this be useful, right? For example, I can use this as a pre-solve technique, right? So you can give me an instance of vertex cover. I can find an optimal solution to its LP relaxation. I can look at the components set to 0 and 1 in this optimal solution and fix those variables to those 0, 1 values. And then I can recurse on the subgraph induced by the variables with fractional value. Now, it's not too hard to see that if I use branch and bound to solve vertex cover, every node in the tree corresponds to a vertex cover instance on a subgraph of the original instance. Right? So ideally, we want to keep using this persistency property as we progress down the tree. One way to do this would be to design a specialized implementation of branch and bound, where we do this fixing and resolving at every node. However, we find that strong branching naturally incorporates this property. And this ability of strong branching is the key to the proof of the fixed parameter upper bound of theorem 1 in the previous slides. Okay, so strong branching in this case really implicitly takes advantage of the problem structure provided by like the vertex cover LP relaxation. Okay. Now, switching gears a little bit, from a computational perspective, maybe I can take any clarifying questions on the vertex cover stuff, since we'll move to different legs of the talk now.
If you have any questions, feel free to post in the chat if there are any quick clarification questions. Okay, I have a very quick one. Does the proof rely on the node selection rule being best bound, or does it not matter?
It does. It does rely on the node selection.
Okay.
Yeah. Good
Does
question.
it? Do you assume that the best bound, the bound is the actual value of the node's LP relaxation or its parents? Because in computation, you don't have the nodes on the frontier, you don't have their LP bounds because you haven't opened them yet. You only get the bound when you open the node. So the solvers usually rely on the parents. So the parents you have, because you've already branched on it, and the two children have an equal bound. So even if you went best bound, you always need to break that tie. So there's something a little bit sketchy going on there in practice that
Good
I don't
question.
know how. Yeah.
So we do not consider. So here we consider evaluating the LPs of the nodes kind of as you add them to your queue. So as you add them to the queue.
I see. Okay. So in your computational results, you do that.
Yes, correct.
Okay.
Yeah. Yeah, great question. Okay, so now switching gears a little bit, from a computational perspective, we look at instances from a variety of problem classes, and we compare trees generated by different variable selection rules against the smallest tree for the instance, okay? And we compute the smallest tree using a dynamic programming algorithm. To our knowledge, this is the first study comparing these variable selection rules to the smallest tree. In fact, previously, strong branching essentially served as the best benchmark to compare variable selection rules against in terms of size. In this chart, the blue and orange bars are strong branching, and the red and green bars are simpler rules like choosing a random variable or most fractional. And our main finding is that strong branching almost always results in trees at most twice the size of the smallest tree. And as is clear in this chart, these other variable selection rules, on the other hand, can be much worse. Okay. Now, given the previous results, especially the computational results, a natural next question might ask, does strong branching always result in a tree that is within a constant or even polynomial factor of the smallest tree in terms of size? Unfortunately, for strong branching, we find that the answer is no. Okay, so in fact, there exists a 0-1 integer program such that the following hold. There's a branch and bound tree of size 4n that solves this IP. And strong branching results in a tree of size at least 2 to the order n. Okay, so this instance shows an exponential separation between strong branching and the smallest tree. Okay, and I want to briefly describe what this instance looks like, because I think it captures what I think are more interesting phenomena even, and will relate back to the computational results that I just covered. Okay. So let's look at what this instance looks like. Okay, so given any 0-1 IP, Bodur, Dash, and Gunlook give the following construction for an extended formulation, which can always be solved with a branch and bound tree, with a small branch and bound tree, in particular one of size at most 4n plus 1. Okay, so let's call the optimization problem over this extended formulation BDG, and the polytope itself Q. Okay, and this polytope Q lives in dimension 2n, so we're going to add n variables for this extended formulation, and we'll see how we do this now. So here's the construction. For each extreme point x star of P, we construct an extreme point x star y star of Q as follows. Set the ith component of y star to be 1 if the ith component of x star is integer, and set it to be 0 if that component of x star is fractional. Okay, so the ith component of y indicates the integrality of the ith component of x star. Now we can demonstrate this small branch and bound tree that solves this instance. So first we branch on y1. And notice that in the LP corresponding to y1 equals 0, all of the extreme points have x1 fractional. So now here I can branch on x1 and observe that both of these resulting children must be empty. Okay, we continue this procedure, and we get the following tree. Observe that at the rightmost node, it has y1 through yn all set to 1, and therefore has only integral extreme points. And so this is a branch and bound tree of linear size that actually finds the integer hull of Q, and therefore of P as well. Now observe that in the problem BDG, the objective on the y variables is 0. And so strong branching, unlike the small branch and bound tree shown here, will only branch on the x variables, right? The original variables. And so if we set P to be some polytope that's hard for branch and bound, say the cropped cube or like Jaroslaw's knapsack, for example, it's well known that this would result in an exponential size branch and bound tree. And in fact, there's another interesting observation to be made here, right? Observe that all extreme points of Q have integer values on its y components, right, by construction. Yet, to get small branch and bound trees for these kinds of instances, we must actually branch on these y variables. And this is quite unintuitive, that at some node of the branch and bound tree, we would find a basic solution to the LP and branch on a variable that has an integer value in that solution instead of one that has a fractional value. Now, of course, one could argue that these are kind of weird instances, and maybe this phenomena doesn't really happen in practice or in typical IPs. But in fact, in our experiments, notice that strong branching doesn't perform relatively as well for these general packing and covering IPs, the top couple of bars here. And in fact, we find that the smallest trees for these instances do branch on variables with an integer value quite frequently. Now, this might be an interesting area of further study, since I don't, I'm not aware of that much has been done to consider branching on variables with integer values in the optimal solution returned to you by the LP solver. Right, so one might consider when it makes sense, when it definitely doesn't make sense, and what the associated consequences of such a branching rule might be. Okay. Finally, I want to mention some other potentially exciting directions for future work. I'll be quick here. So in this talk, we quantified in several ways how strong branching performs well for vertex cover. And it would be great to study the success of strong branching in more generality. So one maybe baby step, maybe not baby step, is recall that the positive results were largely due to the properties of the vertex cover LP relaxation, right? In particular, half integrality and persistency. Iwata, Wallstrom, and Yoshida give a somewhat general framework to get half integral and persistent LP relaxations for several combinatorial optimization problems. And so it might be interesting to show that strong branching performs well on IP formulations constructed via these techniques, since this would apply to a broader class of problems than just vertex cover. Okay. And for another interesting direction, at the end of the talk, we saw that Bodur, Dash, and Gunluk give this construction showing that for any 0-1 IP, there's an extended formulation that branch and bound can solve really quickly in order n nodes. Now, in general, this extended formulation will have a very, very large description, and so linear optimization over this extended formulation may be hard. But this gives rise to the following line of questioning. What more can we say about this relationship between extended formulations and branch and bound? Is there an interesting class of problems for which I can get compact extended formulations that admit small branch and bound trees? And this is maybe a specific example where this might be worth some study. Okay. And I can talk in more detail about the future work, maybe in the breakout rooms, and we can save that time now. Yeah, so finally, I'd like to end by keeping up a summary of the results presented in this talk. But with that, I'm happy to open up to questions.
Okay, great. Thanks a lot, Yatharth. I know I'm going to ask you some more questions later.
Absolutely, I look forward to it.
But there's one maybe quick question, if Georgina doesn't mind, in the chat that maybe you can answer. So Krunal asks, so is it just the strong branching or any branching rule used in practice that branches on fractional variables will result in an exponential size tree for that instance that you constructed?
Yeah, it's the latter. Any branch and bound tree, like the ones used in practice that branch on fractional variables, will require exponential size for those instances. Yeah.
Okay, great.
Yeah, great.
All right. All right. Thank you very much, Yatharth.
Okay, thank you.